Hello, so in this video, we're going to prove the division algorithm, okay? In a previous video, we learned this statement and we learned how to use it. And today our goal is to understand the proof. And this proof is different than previous proofs we've seen in our class. Those proofs have been very short and all sort of can be proved using our little direct proof poem where we can use, basically we can do the proof by just applying a definition and using a short computation and applying a definition again. This proof is going to really require some interesting ideas that might seem like they come a little bit out of left field. But what I want you to see is that this is an example of an existence and uniqueness proof. It's something we haven't seen before, but it's an example of something you may see again, right? And so the first time you see something, it seems wild and creative. The second or third time, it starts to seem like a method, something that you have experience with. Okay. So one of the special ingredients in this proof is the well-ordering principle, which we saw when we first talked about logic. And this is that every non-empty subset of the natural numbers has a smallest element. So this is a special property of the natural numbers that isn't true for the integers or the real numbers or the rational numbers, okay? And we're gonna prove a special case of the division algorithm for when A is positive, all right? So before we get into the proof, let me remind you with a diagram how we're thinking about the division algorithm. Okay, so just recall, oops, let me get my pencil there. Recall that we were thinking about the division algorithm using a diagram like this, where if we have 0 here and A here, the way we find, how do we think about the QB? Well, we look at multiples of B, B, 2B, 3B, here's QB, and the next one is Q plus 1B, etc. So we said that QB in the division algorithm is the multiple of B that's closest to A, but still to the left of A, so that the next multiple of B, which is Q plus 1B, has to be to the right of A, and this one is equal to the smallest multiple of B that's to the right of A or greater than A, okay? And so this diagram, if you have this in your head, it's gonna make the proof a lot easier to understand. So let's see the proof now. So I said this proof is different than our previous proofs. We're not just gonna start by writing down a definition. We're gonna start by, or using one of our definitions. We're gonna start by creating something to talk about, okay? So the thing we're gonna create is a set. So let's let capital B equal the set of all multiples of B such that KB is bigger strictly than A. Okay, I want to apply the well-ordering principle to this set in a minute, but first I need to know that this set is non-empty. So to see that capital B is not empty, note that 2AB is definitely greater than A. So A is positive, so 2A is greater than A, and 2A times B is greater than that. So 2AB is greater than A, and is an integer, okay? 2AB is a multiple of B. So 2AB is in capital B, right? So it's not empty. So I can apply the the well ordering principle and say by the well ordering principle, then B has a smallest element. Okay, and I want to give a name to that smallest element, and I'm going to be really clever. I'm going to look at this picture that we drew, okay? And the picture says the smallest multiple of B that's greater than A, it will be handy for us if we call that Q plus 1B. It has the smallest element, and we're going to call it Q plus 1B. There exists one, and we can call it this, okay? So now since Q plus 1B by definition is the smallest multiple of B that is greater than A, QB has to be less than or equal to A. So QB is less than Q plus 1B, so it has to be less than or equal to A. And now I'm going to say let R equal A minus QB, okay? And if I've done that, so then if I rearrange that equation, I can see that A is equal to QB plus R. So that's what I wanted, right? I wanted to find a Q and an R such that A was equal to QB plus R. I also have to make sure that the R is a possible remainder. So note, note how big can R be, okay? So that since we had that QB is less than or equal to A, and that's less than Q plus 1B, and then how big can this be, right? So let's subtract off the QB from this. So this implies that 0 is less than or equal to A, oops, that's an A minus QB is less than Q plus 1B minus QB, i.e. 0 is less than or equal to A minus QB, and the QB's cancel here, and I just left in B, right? But this was equal to R. So R is even a legit remainder, okay? So I have found that a Q and R from the theorem exist. So therefore, we have A, Q, and R for the theorem statement. Okay, and now we have to prove that this Q and R are unique. So this is really a standard thing that we're going to do. It's just the first time you've ever seen it, okay? So we're gonna say, suppose, well, this is really a proof by contradiction now. Suppose for contradiction that there were another one, okay? Suppose there exist, and I'm gonna give them names Q prime and R prime in Z, such that A is equal to Q prime B plus R prime, and R prime satisfies, oops, the properties that a remainder has to have, okay? So now I have two ways of writing A. So A is equal to QB plus R, which is equal to Q prime B plus R prime. Okay, so I have to show you that the R and R prime are the same, and the B and the Q and the Q prime are the same. So, well, if they're, you know, R and R prime are both numbers, and one of them has to be bigger than or equal to the other without loss of generality. So let's just assume, oops, we can say that we assume without loss of generality that R prime is bigger than or equal to R. And that'll just help me to figure out which side to subtract and make it all look a little neater. Okay, so assume that R prime is greater than or equal to R. So I'm going to subtract the QB plus R from the other side and say that I get then 0 is equal to Q prime B plus R prime minus QB plus R. And oops, I'm just trying to erase that. Okay, and so now I'm going to do some algebra. I'm going to say, well, really this is saying that I have Q prime minus QB plus R prime minus R over here. Okay, so I have that. And now, oh, maybe what I should do, actually, let me take that period back. Maybe I'll put the period in, but this also implies that, let's see, do I want to do it this way? Let's move this, hold on. All right, I decided this will be a little neater algebraically if I backtrack and make a different choice when I do my subtraction. So I'm just going to erase, all right? This isn't the end of the world. Things happen when you're proving, right? And I'm going to take that equation, that QB plus R equals Q prime B prime plus R prime, and I'm going to put the B's on one side and the R's on the other, all right? So what do I mean by that? I mean, I'm going to say, then, if I have QB plus R equals Q prime B plus R prime, I'm going to subtract the Q prime B from both sides, and I'm going to have QB minus Q prime B, and I'm going to subtract the R from both sides so that I have R prime minus R, and on the left-hand side, this is going to look like Q minus Q prime B equals R prime minus R. That's a little better. Okay, so what I have here on the left is a multiple of B, and on the right is R prime minus R. Now, since R and R prime are both less than B, when I subtract them, I get something also that has to be less than B, right? So since R prime and R are bigger than or equal to 0 and less than B, R prime minus R has to also be bigger than or equal to 0 and less than B. So the only way R prime minus R could be a multiple of B is if R prime minus R is 0. So therefore, if R prime minus R is a multiple of B, it must be 0. But what does that mean? Thus, R prime minus R equals 0 which implies that R prime equals R. Here's where I'm going to use that word moreover again, right? I never use that in real life. Moreover, if R prime minus R equals 0, it must be that Q minus Q prime B equals 0, which implies that Q minus Q prime equals 0, which implies that Q equals Q prime. So wait a minute, let's step back. That's like a lot of algebra, a lot of stuff happened. What's happened here, I'm going to switch colors in my pen, is that in the second part of this proof, I said, suppose there exist other integers q prime and r prime such that a is equal to q prime b plus r prime, and r prime is a possible remainder. And when I do that and do this algebra, what I see is that actually the q prime has to be the same as my q that I found in the first part of my proof, and the r prime has to be the same as my r. So in fact, my q and r are unique, and we're done. Okay, so let me just switch back. So phew, we can say, therefore, we conclude that indeed there exist unique Q, R, and Z with R in the form of a remainder such that A is equal to QB plus R, and we're done. Okay,